Hello grade 12s, my name is Tuto Masudubele and today we will be revising probability, grade 12 probability. So what we will be doing is to go over some of the main concepts that are assessed at the end of the year in paper 1. So I hope you enjoyed today's presentation. Now without any waste of time, let's get into our presentation. Now, as I said, we'll be dealing with probability. Probability is a topic that has been allocated around 15 marks in your paper 1 at the end of the year. So I hope that this presentation will help you obtain as many marks as possible in this particular topic. Now, the topic overview for probability, grade 12s, starts from grade 10. Now, in grade 10, under probability, we compare the relative frequency of an experimental outcome with the theoretical probability of the outcome. What also was being done in grade 10 is that Venn diagrams as an aid to solving problems related to probability. We also dealt with mutually exclusive events and complementary events, and we also applied or used the probability identity to help us solve problems that are related to probability. And then in grade 11, we dealt with dependent and independent events, as well as Venn diagrams, contingency tables, as well as tree diagrams. Those are the topics that were mainly assessed in grade 11. And then in grade 12, the generalization of the fundamental counting principle. So that's one of the main topics that you did in grade 12 under probability, as well as probability problems using the fundamental counting principle. So in a nutshell, what I will be doing is just go through past exam questions that are under probability. So one of the first questions, one of the main concepts that are being assessed under probability is what we call the probability identity. Now, before we delve into this question, grade 12s, just a few things for you to remember when you deal with the probability identity. Now, when you deal with the probability identity, there's an equation that we use or that we apply to help us solve problems regarding this. So it says the probability of A or B is equal to the probability of A plus the probability of event B minus the probability of event A and B. So this is the equation that we normally use when working with problems that are related to the probability identity. And also what's very important, grade 12s, under the probability identity, we have what you call mutually exclusive events. We have what you call mutually exclusive events. Now, when we deal with mutually exclusive events, we deal with probabilities that have no intersection. There is no intersection between these two probabilities, so therefore it means that the probability of A and B will always be equal to 0 if our events are mutually exclusive. Whenever you're dealing with mutually exclusive events, remember that the probability of A and B is 0 because there is no intersection between the probability of A and the probability of event B. A and B can represent any two events. For as long as we're trying to find the probability of those two events, and if they are mutually exclusive, remember that the probability of A and B will always be 0. And then we also deal with independent events. We also deal with independent events, particularly questions that are related to the probability identity. And with independent events, it means that the probability of A and B will always be equal to the probability of A multiplied by the probability of B. So when we deal, grade 12s, with independent events, make sure that you read your statements thoroughly. When you deal with independent events, it means that the probability of A and B is equal to the product of the probability of A and the probability of B. Remember that. Mutually exclusive, A and B is 0. Independent events, A and B is equal to the probability of A multiplied with the probability of B. So that's quite important for you to always remember when we deal with questions that are related to the probability identity. Now let's go back to the first question that was taken from the supplementary paper written in 2017. It says here that the events S and T are independent. So immediately by them telling us that events S and event T are independent, we know that for independent events, the probability of those two events will be equal to the product of the probabilities of those independent events. Remember that. Always remember that, grade 12s. Now here they told us that the probability of S and T is equal to a sixth, and then the probability of S is a quarter, and then in 10.1.1 they require us to find the probability of T. Now, because we're dealing with independent events here, remember, let me just go back here. Because we're dealing with independent events for 10.1.1, we know that for independent events, the probability of S and T will be equal to the product of the probability of S multiplied by the probability of T. Then we substitute accordingly into our equation. And if you notice here, we're given the probability of S and T. It's a sixth. So that's what we'll have here. We'll have a sixth will be equal to the probability of S is a quarter. Substitute into your equation. And then we don't know the probability of T. So we leave it as an unknown. And then all we need to do is to isolate for the probability of T. And then after dividing both sides by a quarter, the probability of T will therefore be 2 over 3, 2/3. Why particularly this equation, grade 12s? Because we were told that event S and event T are independent. Okay, now in 10.1.2, hence calculate the probability of S or T. Now to find the probability of S or T, we now make use of the probability identity. Remember I wrote down the equation when I started this presentation. We're going to make use of the probability identity to find the probability of S or T. So the equation reads as such: the probability of S or T is equal to the probability of S plus the probability of T minus the probability of S and T. And now that we know the probability of S, we also know the probability of T, and we also know the probability of S and T because we found it in 10.1.1. Remember that events were independent. All we need to do is to substitute into the equation. And if we substitute into the equation, we'll have a quarter. The probability of S is a quarter plus 2/3 minus, the probability of T is 2/3, and then minus a sixth, and then minus a sixth. And then after simplifying that, you'll find out that we get to the answer of 3/4. We get to the answer of 3/4. And again, just one thing that I need to make you aware of, grade 12s. Probabilities can be expressed as a rational number, meaning a common fraction, or as a decimal fraction, or as a percentage. So you are allowed to leave your answer as a fraction, or a decimal fraction, or a percentage. Be aware of that. Those are the three ways in which we can express probability. So this was a question, grade 12s, that made use of the application of the probability identity, particularly the concept of independent events in relation to the probability identity. Remember, they can also tell you, if they said that these two events are mutually exclusive, if they are mutually exclusive, and they wanted you to find the probability of S or T, if the two events were mutually exclusive, then we know that in the probability identity, if they are mutually exclusive, the probability of S and T will be 0. Remember that. Remember those keywords when dealing with these types of questions. Now I think we can move on to the second question that deals primarily with tree diagrams, which were taught quite extensively in grade 11. It says the following, says the success rate of the Fana soccer team depends on the number of factors. The fitness of these players, the fitness of the players is one of the factors that influence the outcome of a match. The probability that all players are fit for the next match is 70%. Remember when I said probabilities can be expressed as a common fraction, as a decimal fraction, or as a percentage. So in this case, they're giving us these probabilities as a percentage. Bullet number 2 says if all the players are fit to play the next match, the probability of winning the next match is 85%. Bullet number 3, if there are players that are not fit to play the next match, the probability of winning the match is 55%. Based on fitness alone, calculate the probability that the Fana soccer team will win the next match for 5 marks. So what they want us to do here is to find the probability that this soccer team will win the next match based on these factors. Now this is an example of a dependent tree diagram. This is a classic example of a dependent tree diagram. Why is it dependent? Because the probability of one event depends on the other. So what do I mean by that? In order for this soccer team to win a particular match, that is being based on the fitness level of the players. So fitness affects the probability of winning a match. It's a classic example of a dependent tree diagram, and we'll delve right into it and check how the structure of this tree diagram will play out. So, how do we start with the structure of this particular tree diagram? Well, remember, there are two events here. There's fitness and there's the likelihood of winning a match. So what depends on the other? As I said a few moments ago, winning a match depends on the fitness of the players. So it means when we start our tree diagram, first start with fitness. What do I mean by that? It's either the players are fit or they are not fit. So that's the first event. It's either the players are fit or they are not fit. And then what's the second event? Well, winning the match depends on the level of fitness. So, if the players are fit, there is a certain probability of them winning the match. But remember, that probability is not 100%. Because it says here in the first bullet, the probability that all the players are fit for the next match is 70%. So it means not all, the probability of them being fit is not 100%. That's why you have fit and not fit. And if you check here, it says if all the players are fit to play the next match, the probability of winning the next match is 85%. What does that mean? It means there's still a chance of them losing that match, even though they're fit. So that is why we'll have them winning a match, the probability of them winning the match when they're fit, but there'll also be the probability of them losing the match when they are fit. So be careful on how this tree diagram plays out. And then let's go to them being not fit. If they are not fit, is there a probability of them winning the match? Yes. Let's go back to our statement here. The third bullet says, if there are players that are not fit to play the next match, the probability of winning the match will be 55%. So it's a significantly lower probability of them winning the match when they're not fit. So even when they're not fit, they still have the likelihood of winning the match as well as the likelihood of not winning the match, losing, L for losing. And now we have the structure of our tree diagram, which is quite important, but we're not done yet. Because from the structure, we'll then have to write down the probabilities of each event occurring. So the probability of them being fit, remember it's 70%. So remember, probabilities can be expressed as a fraction, decimal, or percentage. They told us here it's 70%, the probability of them being fit for the next match. So I'll express this probability as a decimal. So we'll have 0.7. Now, what's also important for you to know about a tree diagram is that the probabilities of each branch add up to 1. The probabilities of each branch should add up to 1. So it means if the probability of them being fit is 0.7, that means the probability, even though it was not explicitly stated to us about the probability of the players not being fit, but we know that on each branch, the probabilities add up to 1. So if you have 0.7, subtract 1, you subtract 0.7 from 1. If you subtract 0.7 from 1, you'll get 0.3. 0.3, even though it was not explicitly stated to us. Be careful about that. Right, let's move on. When the players are fit, we were told about the probability of them winning the match, and the probability of them winning the match when they are fit was given as 85%. So winning the match when fit is 85%, so 0.85. And remember what I said about the probabilities of each branch. Probabilities of each branch will add up to 1. Probabilities of each branch add up to 1. So if you have 0.85 here, we subtract 0.85 from 1. So if you subtract 0.85 from 1, you'll be left with 0.15. Now let's move on to when they are not fit. The probability of them winning the match when they are not fit is given as 55%. So not fit, 0.55. And then the probability of them losing the match while not being fit, subtract 1 from that, and we'll have 0.45. So not only must you get the structure correct, also the probabilities on each branch. Very important, that grade 12s. And also what will be helpful to you after having the structure of the tree diagram as well as the probabilities is to write down the outcomes, the possible outcomes. So our possible outcomes after these two events have played out is that they can be fit and win the match. They can be fit and lose the match. They can be not fit and still win the match. And they can still be not fit and lose the match. So not fit and lose the match. So these are our possible outcomes. And to know the probability of each outcome occurring, what you do is that you multiply the probabilities that got you there. So in order for me to know the probability of being fit and winning the match, multiply 0.7 with 0.85. If you want to know the probability of being fit and losing the match, 0.7 multiplied by 0.15. And so on and so on and so on. That's how you get the probabilities of your outcomes. You multiply the probabilities that got you there. Now let's go back to the question. Now that we're done with the structure of the tree diagram, it says here, based on fitness alone, calculate the probability that the Fana soccer team will win the next match. So what we want the probability that this team will win the next match. Now, simply go to your outcomes. Outcomes, very important. So, on which outcomes will this particular soccer team win the match? It's here, them being fit and winning the match. There's also them not being fit and still winning the match. That means what are we going to do? We're going to add the probabilities of these two outcomes. We are going to add the probabilities of these two outcomes. Remember, To get the probability of the first outcome, what do? You multiply the probabilities that got you there. So in other words, what we'll have here, so the probability of them winning, it's this probability of the first outcome plus the probability of the second outcome. So we'll have 0.7 multiplied by 0.85, the product of these two probabilities, plus 0.3, because I need the probability of the third event here. So 0.3 multiplied by 0.55. So plus 0.3 multiplied by 0.55. And then when you do that, after simplification, you will get 0.76 as your answer. You can express your answer as a decimal, or you can express it as a percentage, or you can express it as a common fraction. As a common fraction, it will be 19 on 25. As a decimal, or as a percentage, or as a fraction. Don't have to write all three solutions, all three equivalents at once. No, just one. So I just prefer to write it as a decimal. So that was quite a nice tree diagram question, a dependent tree diagram question where one event depends on the other. Now let's move on to the next question. Let's check what we have here. It's another tree diagram question. And it says the following. It says there are 2 orange balls and 2 yellow balls in a bag. Craig randomly selects one ball from the bag, records his choice and returns the ball in the bag. He then randomly selects a second ball from the bag, records his choice and returns it to the bag. It is known that the probability that Craig will select 2 balls of the same color from the bag is 52%. Calculate how many orange balls are there in the bag for 6 marks. Now, what is happening here? It's a classic tree diagram question here, but one that deals with independent events. How do I know it deals with independent events? If you read the second sentence there, it says Craig randomly selects one ball from the bag, records his choice and returns the ball in the bag. So after selecting the first ball, he returns it in the bag. So the sample space does not deplete. The sample space always remains the same. So quite important for you to notice. So it means one event is not dependent on the other. It is not dependent on the other. So in a nutshell, what they want us to do here is to calculate the number of orange balls that are in the bag. Well, how do we construct this tree diagram? Well, notice we have orange and yellow balls. That means the structure of our tree diagram here for 11.3 starts with, you can either choose an orange or a yellow ball. That represents the first event, when Craig chooses at random a ball in a bag. Can either have an orange or a yellow bag, or a yellow ball. But remember, he chooses again. There are only these 2 colors in this particular bag. So to represent the second choice, he could choose orange as the first ball, and then returns the ball in the bag. And then when he chooses for the second time, what are his options? Still orange and yellow. That represents the second event. Or he could choose yellow as his first ball. And after returning the yellow ball in the bag, what are his choices? Still be orange or yellow. So he can either choose between orange and yellow. And he's choosing how many times? Twice. If you are choosing for the 3rd time, that means your tree diagram will keep on branching out as the number of events increases. So what we have here, we have the first event, and also have the second event. Structure of the tree diagram done. All we need to do now is to write down the probabilities on our branches. Well, how many orange balls do we have in this particular bag? If you check the number of orange balls, we have T number of orange balls. That means what we'll have here, we'll have number of orange balls, which are T, over the sample space, as they did not tell us the total number of balls we have here, or the probability of them choosing an orange ball. So we have to express our probability as our favorable outcome over the sample space. Remember, probability in a nutshell, probability of any event, of event A, is the number of elements in of event A over the number of the sample space. That's probability. Favorable outcome, favorable outcomes over the sample space. That's basically probability. So that's what I'm trying to find out here. How many balls, how many orange balls do we have? We have T number of balls. What are the total number of balls? Well, the total number of balls are the yellow and the orange balls combined. And there are T orange balls and there are 2 yellow balls. So all in all, we have T plus 2 number of balls in the bag, depending on what the number of orange balls are. So our sample space will be T plus 2, the total number of possible outcomes. That's our sample space. Now what happens with the yellow balls? How many yellow balls are there? They clearly told us here we have 2 yellow balls. Okay, so we'll have 2 over. That's our favorable outcome. What's the sample space? Sample space, the total number of balls in the bag. We have T plus 2. So we have the first probabilities of our first 2 branches. Now we move on to the second branch. Remember what happens? Craig chooses a ball and then returns the ball in the bag. So our sample space does not deplete as the number of events increases. So that means the number of orange balls in the bag for the second choice will still be T number of orange balls, because they are not decreasing as Craig returns the ball in the bag. If he was not returning the ball in the bag, that means the number of orange balls will decrease by 1. So it will be T minus 1. Over the sample space will also decrease by 1. And that's an example of dependent events. In this case, we're dealing with independent events. The probabilities of the second event do not depend on the probabilities of the first event. So we still have T number of balls for the second choice, and our sample space still remains the same. Same applies with the yellow balls, still remains the same. Still have 2 yellow balls over T plus 2 total number of balls in the bag. Same applies when yellow is being chosen. If yellow was being chosen, our sample space does not decrease as the balls are being returned. So we still have 2 yellow balls over T plus 2. And then for orange, we still have T over T plus 2. However, remember, if Craig was not returning the ball after selecting it for the first time, that means our sample space will therefore decrease, as well as the choice of ball that was chosen in the first event. So be careful about that. Now that we have our probabilities on our branches and the structure of the tree diagram has been made, we need to write down our outcomes. Now outcomes, the first outcome will be 2 orange balls being chosen, orange and orange. So I'll express it as OO. And then the second outcome could be orange and yellow, so O and Y. The third outcome could be yellow and orange. And then we can also have yellow and yellow. So those are our outcomes. And remember, to find the probabilities of each outcome, what do? You multiply. You multiply the probabilities that got you there. So to find the probability of the first outcome will be the probability of the first event, which is T over T plus 2, multiplied by T over T plus 2 to find the probability of the first outcome. Same applies with every other event. Applies with every other event. Now, let's go back to the question here. They say, it is known that the probability that Craig will select 2 balls of the same color, from the bag is 52%. So we know that the probability of him choosing 2 balls of the same color is 52%. And where in our outcomes do we have two balls of the same color? It's two orange balls, or as well as two yellow balls. That means what are we going to do? We are going to add these two the probabilities of these two outcomes, and then equate them, because we already know the answer. The probabilities of these two outcomes is 52%. So we add the probabilities of these two outcomes and then equate them to 52%, and then we can basically solve that basic algebraic expression. So what happens? So the probability of two of those outcomes, so in other words, the probability of two orange balls will be what? Will be t over t plus 2 multiplied by t over t plus 2. That's the probability of the first outcome. Plus, because you can still have two yellow balls, which are two balls of the same color. So it will be here, again, it will be t over t plus 2 multiplied by 2 over t plus 2. So the probability of two orange balls, t over t plus 2 multiplied by t over t plus 2. Remember, multiply the probability that got you there. As well as for two yellow balls, it will be, it's actually 2 over t plus 2 multiplied by 2 over t plus 2. Multiply these two probabilities here, as well as here. So we know that the probability of these two outcomes occurring is 52%. So remember, probabilities can be written as a fraction, decimal, or a percentage. In this case, I'm going to express it as a fraction. 52 over 100 will be equal to, and then we simplify this particular expression. So we'll have here t squared over t squared plus 4t plus 4 plus 4 over t squared plus 4t plus 4. And then we need to simplify. Well, in order for me to simplify, we are adding two fractions here with a common denominator. That means we'll have t squared plus 4 over t squared plus 4t plus 4. We can simplify this fraction here, and if I simplify this fraction, I'll have 13 over 25. And we simplify this particular equation. After simplification, we'll have 25t squared plus 100 will be equal to 13t squared plus, so 13 times 4 will give us 52, and then 13 times 4 again will give us 52. And then since we have a quadratic equation here, we need to write it in standard form. So after writing this particular quadratic equation in standard form, we'll have 3t squared minus 13t plus 12. After simplification, standard form, and simplifying by taking out the common factor, you'll be left with this quadratic equation that's in standard form. And all you need to do is to find the factors of this expression. So to find the factors of this expression, we'll have 3t minus 4 and then t minus 3. We have already equated it to 0. And then all you need to do is to solve for t by applying the zero factor rule. So here we'll have t will be equal to 4 over 3, or t will be equal to 3. But since we are dealing with the number of orange balls, remember t represents the number of orange balls. So that means the set of numbers we are using to express t will have to be natural numbers, because we're dealing with the number of objects, number of balls. So therefore, we negate 4 over 3, and the only solution will be t equal to 3. That means the number of orange balls will be 3. Basically, with this question, it tried to assess your ability to firstly construct a tree diagram, and also for you to know that in order for you to have the probability of selecting two balls of the same color, it's by adding these two outcomes, the probability of 2 orange balls and the probability of 2 yellow balls. After that, it's just a basic algebraic expression that I'm sure any of you can comfortably do to find the number of balls. So this was an example of a tree diagram that dealt with independent events, while the previous one dealt with dependent events. Now let's move on. Let us move on to another question here. This one deals with Venn diagrams. So let's check what's happening with this particular question. It says here that a survey was done among 80 learners on their favorite sport. The results are shown below. We're given all those results there. And the first question is to draw a Venn diagram to represent the above information. Now, if you notice in the information that's given here, we have 3 events. We have rugby, volleyball, and chess. And if you check the second last bullet here, they tell us that X learners like all 3 types of sports. Now, what that tells us, when they tell us that X learners like all 3 types of sports, it means you have the intersection of these 3 events. All these 3 events will intersect as we have a number of learners that like all 3 types of sports. Now let's construct our Venn diagram here for 9.1. Now in order for us to have our Venn diagram, remember all 3 events intersect. So we have the first event, the second event, and the third event. Now the first event will be rugby. Second event will be volleyball. The other one will be cricket. Now, how do we construct, or how do we populate our Venn diagram? Well, in order for you to populate your Venn diagram, first start with the sample space. Remember what our sample space is. We're dealing with how many learners here? We're dealing with 80 learners. So that's the total number of learners that we're dealing with, 80. And then, where do we begin? It's always advisable, Gr12s, always begin with the intersection of your events. Start with the intersection of your events. Remember, this is the intersection of all 3 events. Where I'm pointing at right now on the screen is the intersection of rugby and volleyball only. And this is the intersection of cricket and volleyball only. And this is the intersection of rugby and cricket. Where I'm pointing at right now here, this is rugby only. So what we have here is the number of learners that only play rugby, number of learners that only play volleyball, number of learners that only play cricket. And outside of our events are all the learners that are not part of any of these events. All the learners that are not part of these events go on the outside. It's always advisable, start with the intersection of all 3 events. And they told us here the intersection of all 3 events, we have X learners. So we have X learners here. X learners play all 3 sports. And then it's always advisable, move from the inside and slowly move outward. So from the intersection of all 3 events, go to the intersection of 2 events. And then you go to the regions where learners play one particular sport, which is rugby only, volleyball only, and cricket only. Now, what are they telling us here? If you check this particular bullet here, they tell us that 14 learners like rugby and volleyball, but not chess. Rugby and volleyball, but not chess. 14 learners. Rugby and volleyball, but not chess. It's this region. So how many learners? We have 14 learners. We have 14 learners there. Remember, they like rugby and volleyball, but not chess. It's quite explicitly stated to us here. They include learners that do not like chess. And then we have 12 learners that play rugby and chess, but not volleyball. Rugby and chess, but not volleyball. Rugby and chess, but not volleyball. We have how many learners? We have 12 learners. These learners are learners that do not play volleyball as well. It's quite important. And then we have 15 learners like volleyball and chess but not rugby. So volleyball and chess but not rugby, we have 15 learners here. These include learners that do not play rugby, so they're not part of the rugby event. And then, what else are they telling us here? First bullet here says 52 learners like rugby. Remember, or it's quite important for you to know that 52 learners like rugby, and they did not say 52 learners like rugby only. Remember, let's go back to our regions. This is rugby only, this particular region here or section. So what they told us, they said 52 like rugby. It means the entire event of rugby should be a total of 52 learners. But already in this rugby event, I have 14 learners that also still play rugby, which are part of the 52. I have X learners that are part of the 52, and I have 12 learners that are part of 52. So in order for me to find out how many learners just play rugby, what do I need to do? Is to subtract from 52, subtract 14, X, and 12 to get the number of learners that play rugby only. So if you take 52 minus 14 minus X minus 12, that will give you 26 minus X. Now let's move on to volleyball. 42 learners like volleyball. Again, it means the entire event of learners that like volleyball should be a total of 42. But already in the volleyball event, I have 14 learners, I have X learners, and I have 15 learners. So what do? From 42, we subtract 14, X, and 15. And if you do that, we'll be left with 13 minus X. Now let's move on to the other bullet. They tell us here that 5 learners like chess only. Aha, see, that word is there. 5 learners like chess only. So what they're telling us the exact number of learners that only play chess. Whereas in the first 2 bullets, that was not stated to us. So only 5 learners play chess only. So I can confidently write 5 in the region of chess only. So be careful about those words. They'll help you populate your Venn diagram correctly. And now let's check if there are any learners that don't play any or don't like any of these 3 sports. And they told us here we have 3 learners. 3 learners do not like any sport. That means those 3 learners go outside of our events. So what we've done is to populate our Venn diagram. Remember what I said? It's always advisable, start from the inside, so the intersection of all 3 events, and then slowly move outward. Slowly move outward. So from 3 events, go to 2 events, go to 1 event, and then go to the outside of all your events. Now, let's look at the next question. 9.2 says that show that x equal to 8. So in other words, we need to solve the value of x, which are these 3, which are learners that like all 3 sports. So how are we going to solve that? Remember, when you construct your Venn diagram, it means every single value inside your Venn diagram should be equal to your sample space. To our sample space. That means when I add all the number of learners here in every single region, should equate to 80 learners. So it's a basic algebraic expression or algebraic equation that we are going to use here. We know that all these 80 learners will be the sum of all our events inside our Venn diagram. So we'll have 26 minus x plus 14 plus x. So it's this plus that plus that plus that. So I'm adding all the number of learners, and I know that there should be 8 of them. And then here plus 12 plus 5 plus 15 plus 13 minus x, and then plus 3. All these number of learners should equate to 80. And then all we need to do is to solve this equation. And then as we solve this equation, negative x plus x is 0, and then we'll be left with negative x. And then if you add all these constants, they will amount to 88. And then add the additive inverse of a negative x both sides, as well as the additive inverse of 80 both sides, and then we'll have x equal to 8. So that's a quite easy algebraic expression for us to solve. Now, 9.3. How many learners like rugby only? How many learners like rugby only? Let's go to the region of rugby only. This is our region of rugby only. We have 26 minus x. But now that we found the value of x, so we know we'll have 26 minus 8, as we know the value of x. So 26 minus 8, and that will give us 18. So 18 learners like rugby only. Next question says here, calculate the probability that a learner chosen randomly likes at least 2 different types of sports. Likes at least 2 different types of sports. At least 2 means 2 or more. 2 or more. At least 2 or more. So it can be 2 or 3 sports. Because of the word at least, meaning we have the minimum of 2 sports. So let's go back to our Venn diagram. Regions where we have learners that like 2 or more sports. It's these 14 learners that like rugby and volleyball. These 15 learners, cricket and volleyball. These 12 learners, rugby and cricket. As well as these learners, which are 8 learners, because they like all 3 sports. Because they said at least 2, means a minimum of 2. So, and the question, just going back to the question says, calculate the probability. Probability. Remember, when you deal with probability, we deal with number of elements in event A over the number of elements in the sample space. Favorable outcome over the sample space. So, what's our favorable outcome? It's the addition of all these learners here. So, we'll have for 9.4, we'll have the probability will be equal to 14 plus 15 plus 12 plus those 8 learners, which is the value of x, divided by, so this is our favorable outcome. What's our sample space? Sample space is 80, the total number of possible outcomes. So we'll have 80 there, and then after simplification of this expression, we'll have 49 on 80. Fraction or a decimal or a percentage, it's all fine. We accept that as a valid answer. So, quite a nice question that deals with Venn diagrams. I hope it was clear on how we construct a Venn diagram. Please make sure that you read your information correctly and you populate the Venn diagram correctly. Now, one last question, grade 12s, that deals with the fundamental counting principles. And it reads as such. It says here that a 5-digit code is created from digits 2, 3, 5, 7, and 9. How many different codes can be created? If, so here they're telling us if repetition of the digits is not allowed in the code. Repetition of the digits is not allowed in the code. So, we are trying to create a code here, grade 12s. Trying to create a code. That's a 5-digit code from these digits. So 5-digit code, 1, 2, 3, 4, 5. Now we want to find out the number of different codes that can be created if we are not allowed to repeat a digit. So whatever our code is, can have more than one of the options that are given here. So I'm going to have more than 1, 2, or more than 1, 3, and so on and so on and so on. So, how do we go about this question? Now, with the fundamental counting principle, the key factor is all about the number of options you have on placing at a particular placeholder. So, as we start this code, which is 10.2.1, as we start this code, That means out of all my options that I have here, how many options do I have to place in my first placeholder? I have 1, 2, 3, 4, 5. So it means I can put any of the 5 options in my first space holder, or any of the 5 digits can either start with the 2, with the 3, the 5, the 7, or a 9. Any of the 5 digits. But once I use any one of them, and remember, repetition is not allowed. Repetition is not allowed. So if I use one of the digits here, see now I placed a 9 as my first option. That means how many options do I have left? Because I can't use that 9, I'm left with what? 4 options. Left with 4 options. And again, if I place another digit here, any of the 4 digits that are remaining, if I place another one, how many are left? I'll be left with 3. And then if I place another one, I'll be left with 2, and then I'll then be left with 1. And what's important is the product of all those options. That will tell me the number of different 5-digit codes that I'll have. So therefore, we'll have 5 multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1. And that will give us 120. Oh, I'm sure you have been taught about the concept of factorial. So it means another way to express the product of these factors will be 5 factorial. And 5 factorial does come out as 120 different codes that we'll have. If repetition is not allowed, Now let's look at 10.2.2. 10.2.2, still want to find the number of different codes that can be created if repetition of the digits is allowed now. Now we're allowed to repeat the digits. Whatever my code is can have as many, meaning all these digits can repeat themselves. I can have 2, 2, 2, 2, 2, or 3, 3, 3, and so on, and so on, and so on, and so on. So still approach it the same way as this one. It's all about the number of options we have. 1, 2, 3, 4, 5. In the beginning, when I start, I have all 5 options, all 5 digits to choose from. So how many options do I have? I have 5 to choose from. After choosing one of the digits in my first space holder, or the first digit of this particular code, after choosing any one of them, do the number of options decrease? If repetition is allowed, no. It means I still have how many options left? I still have 5 options in the second space holder. What happened with the first one? Because repetition is not allowed, as I'm placing a digit, the number of options decrease. The number of options decrease because repetition is not allowed. But because repetition is allowed, the number of options remain the same. So I still have 5 options, still 5 options because I can repeat. Still n of the 5, still n of the 5, still n of the 5. And what's important is that we find the product of those options. So therefore, what we have here, we have 5 multiplied by 5 multiplied by 5. So basically it's 5 to the power 5, and 5 to the power 5 will give us 3,125 different codes. Because here, repetition is allowed. Repetition, not allowed. Number of options, decrease, which with each space holder. Number of options do not decrease because repetition is allowed. Right, now 10.3. It says here that a group of 3 South Africans, 2 Australians, and 2 Englishmen are staying at the same hotel while on holiday. Each person has his or her own room, and the rooms are next to each other in a straight corridor. If the rooms are allocated at random, determine the probability that 2 Australians will have adjacent rooms and 2 Englishmen will also have adjacent rooms. Now in this case, what we're trying to do, we're trying to keep the Australians together and the Englishmen together. So how do you go about this question? Well, what's happening here is that the total number of people we have here, we have 7 people all in all. But now if you check, now there are conditions placed in how these people are going to be placed. 2 Australians always want to be together, and 2 Englishmen want to be together. Now what's going to happen if these 2 Australians want to be together? That means for these 2 Australians, how many different ways can we arrange these 2 Australians if they want to be together? Well, it's only 2 of them, so you have 2 multiplied by 1, number of arrangements. That means in the first room, I can put any of the 2 Australians there, but once I place an Australian in the first room, then that means in the second room I'm only left with 1. Only left with 1. Why are my number of options decreasing here? Because we are dealing with objects, and if we deal with objects, it is inherent that repetition is not allowed. They need not say to you that repetition is not allowed. Dealing with objects, repetition is automatically not allowed if you deal with objects. Human beings, cars, any type of object, repetition is not allowed. So those are the number of options we have for the Australians. And then for the Englishmen, how many Englishmen do we have here? Still have 2. How many ways can I place these 2 Englishmen there? Well, in the first room, I still have 2. I can put any of the 2 Englishmen there, and then in the other one, I can put any, because once I've placed one person in the first room, that means I'm left with only 1 to put in the second room. So these always want to be together. Now, we need to check the number of objects that we have. Remember, we still have those 3 South Africans, which don't need to be grouped together. They can be placed in any room. So because they can be placed in any room, I'm not going to group them. So what we're going to do, we check the number of objects we have now. If you check the number of objects we have these 3 objects, these 3 human beings, plus this 1 object, because the minute you group any 2 or more objects, they count as 1. If I need to find out the number of objects, so it's 3 plus 1 plus 1. So all in all, how many objects do I have? I'll have 5 objects. So multiplied by, remember we have 5 objects, and they can be placed in any order. So because they can be placed in any order, it's 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. So these are the number of objects that are left. So all in all, in order for you to write this in a neater way, what we have is 2 factorial, 2 times 1, multiplied by 2 factorial, multiplied by 5 factorial. What is this? This is our favorable outcome. This is our favorable outcome. Favorable outcome. And then what's our sample space? What's our sample space? The total number of possible outcomes. And all in all, how many people do we have here? We have 7. So we'll have 7 factorial as our sample space. So therefore, the probability will be 2 factorial times 2 factorial times 5 factorial over 7 factorial. And then what we'll have there after simplification will be 2 over 21. After simplification there, what we'll have is 2 over 21. So you need to be very careful, grade 12, especially when dealing with questions relating to the fundamental counting principle. They can be a bit tricky, but I hope this lesson helped you in order for you to prepare for your upcoming November examination. I wish you all the best, grade 12s. Keep on practicing, and I'm sure you'll do well.